In the last video, we studied about the constant volume gas thermometer, and we mentioned an interesting property that occurs when we heat up a gas or some other substance. So, for instance, when we heat up a gas, its volume increases. And this is one very interesting property that we're going to explore today in a deeper meaning. So, today we're going to study about thermal expansion or linear thermal expansion and volume thermal expansion. So, what is thermal expansion? Well, in most substances, and this is very important to note, that in most substances, as we increase the temperature of a gas or liquid or solid, the volume of that substance will increase. So linear expansion only occurs in solids, and that can be written in the formula as LF, or the final length, is equal to the initial length times in brackets 1 plus the coefficient of thermal expansion times the change in temperature. The change in temperature is in degrees Celsius or in Kelvin, but that's not important since a change in temperature in Kelvin or in degrees Celsius will be equal to each other. Now the coefficient of thermal expansion, its unit is degrees Celsius to the power of -1. And this is the final length of the substance after it is heated or cooled, and this is the initial length. So when a substance is heated, the change in temperature will be plus, and as a result, that substance will increase in volume or increase in length. We can also write this in terms as delta L is equal to Li times the coefficient of thermal expansion times delta T. This is the exact same formula, but in this case we can see that if the change in temperature is positive or if the temperature increases, that substance will increase in length, or if the temperature decreases or the substance cools, the length will contract. Now, one very interesting property of water, for instance, is that all other substances that are in a liquid state, their volume increases as we increase in temperature. But for water, the interesting thing is that between 0 degrees Celsius and 4 degrees Celsius, as we increase the temperature from 0 degrees Celsius till 4 degrees Celsius, then the volume will actually decrease, and at 4 degrees Celsius we have the maximum density of that substance. So basically, if we cool water from 4 degrees Celsius till 0 degrees Celsius, then that substance will basically increase in volume. And since we mentioned volume, we're going to move on to volume expansion or volume thermal expansion. So basically we can use the same formula, or delta V is equal to Vi, or the initial volume, times B, the thermal coefficient of volume expansion, times delta T, or the change in temperature. Now again here beta is expressed in degrees Celsius to the power of -1. Okay, so volume expansion happens in all three states, either solid, liquid, or gaseous state. Now what I want to do is talk about isotropic substances, or substances that expand as the temperature increases, but their expansion is equal in all three directions, or on all three axes. So how can we find the relationship between alpha and beta, or the coefficient for linear expansion and the coefficient for volume expansion? Now let's say we have a solid substance, and let's say that we can express the final temperature as Ti plus delta T. The final volume can be expressed as Vi plus delta V. Okay, so according to this, Vi, or the initial volume, will be equal to the length times the width times the height of that substance. Okay, so how can we express the final volume, or the volume after the change in temperature? Well, we can write, since the final volume is Vi plus delta V, we can write this as L plus delta L, or the final length, times H plus delta H, and then times the width plus the change in width. Okay, so this will be here the final volume. Now what we can do is, since the substance is isotropic, we can express the deltas in terms of the formula that we had just seen, and we can rewrite this. So let me just delete this and we'll continue. So we have that Vi plus delta V is equal to L plus, now the change in length will be equal to L plus L times alpha times delta T, then the width plus the initial width times alpha times delta T, and then times the height plus the height times alpha times delta T. Okay, so what we can do here is we can take in front of the brackets L, the length, the width, and the height, and what we'll get is 1 plus alpha times delta T, and basically we're going to get that in all cases. So if we put LW and H in front of the brackets, we will get 1 plus alpha times delta T to the power of 3. Okay, so basically we can expand in these brackets, and basically to make it a little bit shorter, we will say that alpha times delta T is very smaller than 1. So we have alpha times delta T to the power of 2, or to the third power. We can neglect that. So if we do the expansion in the brackets, what we will get in the end is that beta is equal to 3 alpha. Okay, so that's all for thermal expansion. In the next 2 videos we're going to solve some problems regarding thermal expansion, linear thermal expansion, and volume thermal expansion, and we're going to use the knowledge that we gained today.